So this is the fundamental theorem of calculus part 2. If you did not watch part 1, please go back and do so. So we're continuing on with these examples, and the directions for example 3, part A and B, say to evaluate the definite integral using the fundamental theorem of calculus. Okay, so first things first is we got to find the antiderivative. Okay, so I find the antiderivative. I'm going to pop out the 5 because that's coefficient, and I'm going to take the derivative of e to the x, which is my favorite, e to the x. Now I'm going to take and evaluate that from ln2 to 3. Okay, so my next step, so step number 2 is find f at b minus f at a. So f at b, we're going to plug and play. So 5 times e to the third, and that's it. Okay, f at a, I'm going to find that. So I have 5 times e to the ln2. I don't know if you guys remember from algebra, but e to the ln2 is just 2. So this becomes 5 times 2, which is 10. All right, number 3. Now we're going to subtract. So we're going to subtract f at b minus f at a. And when I subtract it, I get 5e to the third minus 10. Now you're going to need a calculator to do this. And I'm going to run it through the calculator just to make sure my calculations and my notes are correct. So I'm doing this with you guys. So 5e raised to the third power, and then minus 10. And I got 90.43 because I rounded to the nearest hundreds place. And that's what I have in the notes. All right, so let's do part B. Again, evaluate the definite integral using the fundamental theorem of calculus. So first we have to find the antiderivative. So to find the antiderivative, remember that I can break this up into 1/2 from 1 to 1/2 of 1 over x dx. And I know the antiderivative of 1 over x is ln x. Okay, so we're going to write that up. So this antiderivative is 1/2 ln x. And guys, instead of the soft parentheses, I believe that we're supposed to use absolute value there. It'll be a positive value, so that won't be a problem. But we're going to evaluate this from 1/2 to 1. So 2. Second step, find f at b minus f at a. Okay, so I'm going to find f at b first. So I'm going to plug in the value of 1. So this is 1/2 ln of 1. And I don't know if you guys remember that ln of 1 is 0. So 1/2 times 0 equals 0. F at a, 1/2 ln at 1/2. Now we're going to get an actual value. So what I'm going to do is plug that into my calculator. So 1/2 or 0.5 times ln of 0.5. And when I do that, I get negative 0.3466. Again, I'm just rounding it. So 3, I'm going to take f at b minus f at a. So I have 0 minus a negative 0.3466. And this is going to give me a positive 0.347. I'm just rounding again, guys. Okay, so that's how you do that one. Let's look on to the next example, number 4. Evaluate the definite integral using the fundamental theorem of calculus. So as mentioned before, if you have a quotient, you either have to work on it or you have to see if it matches up with something. So lucky for us, there's the rule that says integration of 1 over the square root of 1 minus x squared dx. The antiderivative of that would give me inverse sine. So we lucked out that we have a rule for it, so now I can continue on. So the antiderivative is inverse sine. And we're evaluating that from negative 1/2 to positive 1/2. Okay? So number 2, find f at b and f at a. So the antiderivative at b looks like this. Inverse sine at 1/2. Okay, so basically I'm looking for an angle. What angle will give me the value of sine at 1/2? And if you look on the unit circle, you'll find that 1/2 happens at pi over 6. Okay? F at a, inverse sine of 1/2 positive, or negative, sorry, a is negative because the lower limit. If I plug that in, I get negative pi over 6. Because remember, inverse sine's range is from negative pi over 2 to positive pi over 2. So I need quadrant 1, which is pi over 6. Quadrant 4, and when I say that, I'm saying that in air quotes because it's not really quadrant 4. It's negative values. Okay? So I found those 2, and 3, I have to subtract them now. So f at b minus f at a. So f at b is pi over 6 minus f at a, which is negative pi over 6. And when we add these together, I get 2 pi over 6 or pi over 3. So that is my answer to that problem. And finally, I think this is the last one of the section. We have another trig function where we're asked to find the integration from 0 to pi over 3 of secant x. So the rule for this, the integration of secant x dx, gives us ln of the absolute value of secant x plus tangent x. Okay, that is the rule. All right. So, 1, the antiderivative. And by the way, I should have plus c there, so I'm going to do that. The antiderivative is going to be ln secant x plus tangent x. And then I'm integrating it from 0 to pi over 3. Okay? 2, find f at b and f at a. Okay? So f at b, we're going to do that one first. B equals pi over 3. So the ln of secant at pi over 3 plus tangent at pi over 3. So guys, just to make life easier, I am going to draw a triangle just so I can see some stuff here. So 30 degrees, remember, is pi over 6. And 60 degrees is pi over 3. Okay, so here's 30 degrees, here's 60 degrees, here's the right angle. And here's the values, okay? I'm looking for secant of pi over 3. Secant is a reciprocal function of cosine. So secant is hypotenuse over adjacent. So I'm looking at this angle here. Hypotenuse is 2 over the adjacent angle, which is 1. So 2 over 1 is 2. So ln of 2 plus. Now I have to find tangent. Tangent is opposite over adjacent. So opposite is radical 3 over 1, which is radical 3. So plus radical 3. Okay, so when I do that on the calculator, I get 1.32. Okay, that's f at b. Let's find f at a. Remember, a is equaling to 0, so it should be a little bit easier. So ln secant of pi over 3 plus tangent, and I should have wrote 0, so I'm going to fix that because I'm doing f at a. So guys, don't forget that when I'm doing this, I'm using the unit circle, right? So let me move that so it looks better. Okay. All right, so remember the values here are 1, 0 at 0 degrees, right? Or 0 radians. All right, so secant, again, is 1 over cosine, right? So cosine at that value is 1. So 1 over 1 is 1. Tangent, remember, is sine over cosine, right? So sine at 0 is 0, and cosine at 0 is 1. So this becomes 0. So ln of 1, remember, is 0. So now my last step is to take f at b minus f at a. So this should be pretty easy. So f at b, remember, was 1.32 minus f of a, which is 0. So I get 1.32. Okay, so that was a good reminder of trig. All right, and that is the end of the fundamental theorem of calculus.